Internal clock. So today I'm going to cover the Z or Z transform, depending on which way I feel like saying it in that sentence, and then I'll start with the introduction to control theory, and the chapter is online, so you can see it. And as usual, I guess you'll find some mistakes in it, so please feel free to put up the corrections on that. Okay, let me get started with the Z transform. We've been through several different transforms already. We looked at Fourier Series, Fourier transform, Discrete-Time Fourier transform, Laplace transform, and now one more transform. So why? Why do we need all these, and what's the relationship between all of them? And I'm going to basically try and explain to you the need for the Z transform, or really how it fits into the whole picture. So we started out with this notion of a periodic signal, and it's a continuous periodic signal. And if it's continuous and periodic, and infinite, of course, then we get the Fourier series. Okay, and then we go into this notion of, okay, it's aperiodic, so you need one thing, then it's Fourier transform. Except when we have cases where it's not absolutely integrable. So we have some kind of function that goes like this. This is neither periodic nor absolutely integrable. If it looks like this, for example, e to the at, where a is greater than 0, so e to the plus at, a greater than 0, that's the Fourier transform won't work. So for this, so to come back to this, if it's absolutely integrable like this, we can use the Fourier transform. But if it is not absolutely integrable, then what we need to do is this like e to the at, then we need to pre-multiply it with some kind of exponential to kind of bring it down, and we multiply the e to the sigma t, okay, and this gives us the Laplace transform. So one way of thinking of the Laplace is simply that we're pre-multiplying by this exponential, which is exponentially decaying. It's a decaying exponential. Okay, sigma is less than 0, it goes down very fast, and in this case we are able to actually compute the transform for certain values of sigma, which is the region of convergence, and that's the Laplace transform. All three are continuous. Okay. Now in the discrete time case, we have looked at the discrete time Fourier transform. And the discrete time Fourier transform, we sort of have some function. We really don't care whether it's a periodic or aperiodic or whatever, but we can we're going to compute the discrete time Fourier transform as the sum of exponentials, so x and t, e to the j omega k t, k t naught. I think that's right. Okay, and so this is the discrete time Fourier, and then we had the FFT, which was saying that this is this DFT, as we call it, DFT or FFT, where it's either periodic or finite. In which case, we can the summation becomes a limited summation. We only have a discrete number of frequencies to worry about, and so we have the discrete time and frequency Fourier transform DFT, and then the fast way of doing is the FFT. So any questions about this so far? So this set is all continuous, and you can see it differ because here it's periodic, and because it's periodic, obviously each part is going to be absolutely integrable. It kind of comes for sure, guaranteed, because obviously each part is time limited. If it's absolutely integral but not periodic, get Fourier transform, and then you get the Laplace transform. So these three obviously are kind of clear, right? They're different from each other, and this is the most general of the lot. Okay. Here we have similar kind of situation where we actually, this more or less corresponds to the Fourier series. Okay, the DFT, though not exactly because it's discrete. and then that's some function. But we haven't looked at the case where the discrete function is, let's say, diverging. It keeps growing greater and greater over time, right? If we have this, then you could say intuitively we should have some way of pre-multiplying by something like e to the sigma, and by doing so we'll make it converge, right? So we want to take a series or a signal which is naturally diverging, and we want to somehow pre-multiply it and make it converge, which is what the Laplace does. So the question is, what is the equivalent to the Laplace transform in the discrete world? Okay, because in the continuous world, this is sort of the most general, and we can do sort of everything that we want with the Laplace. What can we do in the discrete world? And the answer is the Z transform. So Z is sort of equivalent to the Laplace. So in the same way that so this, remember, is for a finite or periodic. So this is periodic or finite. So this is periodic or finite, and that's periodic, okay? This is finite, and that actually is infinite, but then we really don't have this pre-multiply, and that pre-multiplication is what we're getting to the Z transform, okay? So any questions about it? That's where we're sort of heading towards. And to kind of give the punchline is that when we analyze a system using control theory, which we will shortly, our preferred tools will be Laplace for the continuous domain and the Z transform for the discrete domain, because these are in some sense the most general that we would like. Now, so anyway, I'll put most general in quotes because it's not exactly the most general, but certainly they're more general than the other ones. So any questions about this? Okay. So now you see why there is a need for so many different transforms. Yeah. Did a question do that? No, okay. Okay. All right. So given this, let's see what the Z transform should look like. Given this, what should it look like? Well, it should look like the Laplace. And so let me start with the let me start with the general form of a transform. The general form of transform is basically we have some signal. Okay, we have sigma or integral, depending on what it is, whether it's discrete or continuous. And then the second part of it, so we have some summation or integral. We have the signal multiplied by some kind of pre-multiplier. Okay, this could be e to the sigma t, and then multiplied by essentially a complex exponential, which corresponds to something in the omega, in the frequency domain. Okay, this is sort of the anatomy of a transform. Okay, if you look at Laplace, it's integral xt e to the sigma t e to the j omega t. Okay, and we take sigma plus j omega, we get st, so we have integral xt e to the st. If you look at Fourier series, you have sort of the summation ck, and we really don't have a pre-multiplier, we just have e to the j omega t. Okay, if you look at Discrete-Time Fourier, then we have summation, we have xnt, no pre-multiplier, and we do e to the jk omega naught t. Right? So that's what every transform looks like, okay, that we've looked at so far. And in fact, many other transforms can be put in this exact same notation. So if you use this and you say, okay, how do we do the Z transform? Well, first of all, it's going to be a summation because it's discrete. Okay, we don't have an integral. We have signals, so it's going to look like this, xk because it's discrete, or xnt, doesn't matter. We're going to have pre-multiplier. So let me just leave it as e to sigma t for now. And we have some complex exponential, which will be e to the j omega t. And so we could potentially write this as xk e to the sigma plus j omega t and summation, okay, or j omega k to be more precise, because it's discrete. or sigma plus j omega k. We could write it like this, right? And that would be a perfectly valid definition of the Z transform. Okay. However, it turns out that we know that so a e to the j omega, or in fact to be more precise, any a e to the a e to the b is equivalent to a should I theta equal to a plus jb, right? So anything in the exponential form can be written in the a plus jb form also, right? And if you were to write z equals a to the theta, then the same z can be written as a plus jb as well, right? There's no particular reason why you have to write in one form or the other equivalent forms. And therefore, we could replace this with z equals a plus jb, where a in this case is going to be the magnitude, right? The magnitude is square root of a square plus b square, and the phase angle, okay, which is going to be given by tan inverse b over a. Okay, that's the rules for converting from a plus jb form to the a to the theta form. And so, in fact, we can rewrite this as sigma xk z to the k equals minus infinity to infinity, and this in fact is the Z transform. Okay. So the Z transform, if you think about it, is basically the discrete Laplace transform. Okay, it's Laplace transform applied to discrete, where we have the same signal xk, we have the pre-multiplier, and we have the constant exponential, except these two, which in the Laplace we call e to the st, we are replacing by z. Yeah?
And the power of z should be negative?
Oh, yeah, it does, yeah, so, sorry, yeah, minus k. Yeah, sorry. We always have e to the minus st, so, I mean, these, yeah, sorry. Complex e to the minus j omega t, so whatever, minus sigma t. Yeah. In this case, a would be the a plus jb. It would be a is going to be capital A is going to be square root of positive square root of a square plus b square. That's the magnitude of a plus jb, right? When you think of a phasor, so this is a, this is b, this is a plus jb. This is going to be capital A, and this angle is theta, right? This is capital A, so capital A is going to be square root of a square plus b square, positive square root, so we take the magnitude, and that's the length of the phasor, and the angle is tan inverse b over a, which is what I said, right? So we can convert from one form to the other. And so e to the sigma plus j omega k is basically the same as e to the minus sigma j omega k is same as z to the minus k. Okay. Plus and minus, it's like, it's not really relevant because you can always choose which half plane we want to be in. So just for purpose of exposition, I just wanted to focus on the exponential part rather than the sign. But yes, you're right, it is negative. Okay. Any questions about this? Okay. So hopefully you now have a good intuitive understanding of where the Z transform is coming from. Okay. Because when I was studying it, I was like, oh, wait a minute. The discrete Fourier transform, the DFT is so complicated, right? I mean, it looks like this. Sigma, what is it? K equals 0 to n minus 1. That's a DFT. So x n t, or xk in this case, e to minus j k omega naught t. And saying, I mean, this is so complicated, But now suddenly we just go into just z. That's it, z to the minus k. And it's because of this equivalence over here. These two are the same. Okay. All right, so everybody clear on that? Okay, so now this allows us to make life much easier, and we will use this fact very, very soon in computing the Z transform. So how do we do this? So we define the xk is transformed by the z transform given by, so we'll just consider causal signals, which means that we can assume that there is a uk, so xk is basically equivalent to xk uk. So the uk, the unit step function, is automatically assumed, okay, in this exposition, again, because we're only considering causal systems. So it will be k equals 0 to infinity. We'll ignore the minus infinity. Xk z to the minus k. And then the inverse transform. The inverse transform is a bit complicated, and I'll give you the expression for it. That should not be xt, that should be xk. Okay. xk, right. So xk is given by 1 over 2 pi j. And this is a circular integral, and see, which is, this is xz over here. Sorry, xz is not in square bracket. Xz is a continuous function of time, so x z, oops, this is going to be x. Be careful about the braces. Z to the k minus 1 zz, and this, the circular integral is what's called a path integral, and the path is chosen in such a way so as to encompass all the poles and zeros, but basically you don't need to worry about it, or I should say, as engineers we don't worry about it. We just look at the table, you know, like the engineer has to add 2 and 2, looks at 2 and 2, the table says 4, okay, the answer is 4. Same way, you want to compute the inverse z transform, you look at the table of transforms and you figure out what the answer is, okay. Actually computing this is a pain in the neck, and it's not something that we usually would like to do. I just noticed that there are a couple of typos in the text. The dz should be, I think I corrected that, but it should be xk, not xt on the left hand side, because it's a discrete function of time, and for some reason the z has become capitalized. It should be small z, not a capital Z, on the right hand side of equation 70. So it should be small z. Okay. All right. So what time is it? Okay. I'm just going to do one example and we'll take a break. So let's do the z transform of uk, which is the unit step in discrete time. And so we can do it easily as as xz, sorry, oops, xz equals integral k equals 0 to infinity uk z to the minus k. So this is just 1. Now we have an infinite sum with the z to the minus k, and so we know that this sum is going to be 1 over 1 minus z, okay, if sorry, z 1 over 1 minus if mod z inverse is less than 1 or z is greater than 1, okay. So what does that mean? Okay, what this means is that we have, if you look at the real imaginary plane like so, we have so this is z over here. Z is a complex number. So this is the unit circle. So this value is 1. We have to have z be outside the unit circle. Okay, if it's outside the unit circle, then 1 over z is going to be inside the unit circle, okay, and 1 over z is going to be what we're multiplying over here. This is z to the minus k, right? And so it's going to converge, right? So just to give you an example, if my usual z equals 5 plus j0 for the sake of argument. So over here that's 5. Z inverse is equal to 1 over 5. And obviously 1 over 5, you know, you got 1 over 25, 1 over 125. that sum is exponentially decreasing. We get a converging series, and it's going to be converging. So what do we need for it to converge? We need z greater than 1. Okay, modulus of z. Of course, it can be anything. It can be j something else, you know. So mod z inverse. But it could be any complex quantity as long as that is out there. So remember that the z transform, the value x z over here is a continuous function of z. You know, so we could have, it's a complex function of this variable over here. So it could be anywhere in the plane, and corresponding to that value in the plane, we'll have a different value of the transform because it's a function of this. But the convergence is only assured outside of this unit circle over here. And so in the z transform, we always have this convergence being specified in terms of circles, because we always have mod z, the magnitude of z is going to be less than something, okay? And so what happens is that we'll typically have, you know, the value z should be in some ring, you know, some donut-shaped thing, which in mathematical term for that is annulus. So we have annulus, and in that annulus is where convergence is defined, where the value of z is between two ranges, between two values, alpha and beta typically. Okay. So coming back to z transform, let me do a couple more examples. One is of the discrete exponential. So let's look at the exponential xk. This is a discrete one. It's going to be e to the minus ak. And so this is basically, we have k on this axis rather than t, and it starts at some value, which is, well, it's going to be 1 because k is 0, and it's going to go down like this, etc. So, and then of course when a is less than 0, it goes up like that. So it goes up like that. So what is the z transform of this? Well, by definition, we have x of z is going to be sigma a equals 0 to infinity e to the minus ak z inverse z minus k. And so this can be written as sigma k equals 0 to infinity e to the minus a z inverse to the k, because that's the way exponentials work. And this looks basically like something of the form a to the k, and this is going to converge to 1 over 1 minus e to the minus a z inverse r, which is equal to z over z minus e to the minus a, either one. When, and we have the region of convergence again, when e to the minus a z inverse less than 1, which is equivalent to mod z is greater than e to the minus a. Okay, so again what we have is, we have a sort of a circle. In this case, the radius is going to be e to the minus a, whatever that is. So it's a is 5 with e to the minus 5, and then as long as we choose the quote-unquote pre-multiplication by a value of z greater than that, we're going to be fine. The series is going to converge, right? So what are we really saying? We're saying that this particular exponential is going to be, you know, is it e to the, let me see, a is, yeah. So a could be negative, okay, for example. If a is negative, e to the ak is going to be increasing like so, right? So what we need to do is to make sure that no matter what a is, we're going to be pushing it down fast enough, and that is assured when the value of the magnitude of z is greater than this, okay? And of course, if a is positive, we're in good shape already, but if a is negative, we need to make sure that this is going to be valid, because if a is negative, e to the minus a can be very large. Let's say a is minus 100, this annulus is going to be e to the 100, which is a very, very large area, very, very large ring, right? But z has to be bigger than that to push e to the minus a down, right? E to the 100 is a very large number. So that's fine. As long as you choose z large enough, it's going to converge. Okay. So what about if z equals e to the minus a? If you're on this ring, basically what happens is that this value is going to be infinite, right? If you're on this ring, z inverse is going to be equal to e to the minus a. So this becomes 1 minus 1 becomes 1 over 0, the infinity form, and so that's a pole. So the value of z for which xz equals infinity is called the pole, and then the value z for which xz equals 0 is called the 0. And this is just exactly like the Laplace transform, and really there's not a whole lot more to it. Okay, and you can see that the form actually that we use for computing these transforms is very much like what we had with the Laplace, where we had 1 over 1 minus s. Okay. Now, one thing is that there's a slightly different convention. Some authors or some people try to use z inverse as the transform, and some people give it in z. The equivalent, whatever works for you, it doesn't really matter. The standard form is to give it in the form z inverse, but there's no right or wrong. Either way is what people use. Okay, let me do one more. This is the sinusoidal or discrete sinusoid, and by now the trick for doing this is you should know what to do, which is that whenever you see a sinusoid, use Euler's formula. So we have the complex sinusoid cos omega k. So it looks like this. It's going to be so it's like a sample of a cosine function. Okay, so we take a cosine function, we're going to sample it with some periodicity. That's what it looks like. So we can compute the z transform by rewriting this as e to the j omega k plus e to the minus j omega k by 2, or right. So, and then this gives us basically xz equals, okay, so we can just write it as this, e to the j omega k z to the minus k by 2 plus sigma k equals 0 to infinity e to the minus j omega k z to the minus k by 2. Now, we already saw just now that the z transform of e to the minus ak is given to 1 over 1 minus e to the minus k z inverse just now. So we can just directly write the transform for this as being half of 1 over 1 minus e to the j omega z inverse plus 1 over 1 minus e to the minus j omega z inverse, right? Because it's both cases e to the a, e to the ak goes to 1 over 1 minus e to the a z inverse. So e to the a goes to e to the minus a goes the other way. So we get this basically just kind of automatically. And this turns out to have region of convergence of mod z greater than mod of e to the minus j omega. And whenever you see this, you have to realize that that's just a phasor, right? E to the minus j omega is our basic unit phasor. Its magnitude is 1, right? So we just need to know. So because it's a unit phasor. So don't need to get confused. It's obviously, if you really get confused, you can just think about it, just cos j omega plus j sin j omega. And both of these are going to have values basically less than 1. Okay. So again, we have a region of convergence over here. Now there is this section over here that comes. Are there any questions about this over here? Okay. I have a small section 5.11.1 on the relationship between the z transform and the Laplace transform. It's actually not particularly complicated. The part where it gets confusing is that because the Laplace, because we're taking a sample, this sampling means that we're actually multiplying xt with an infinite impulse train. Or rather, I should say, well, it's infinite, but only in one direction. It's only in the positive, it's 0 after this. But at any rate, that results in the convolution being repeated over and over again, because we have this property that when we convolve any signal with an impulse train, we're going to have the replication of the transform over and over again. And that makes it a bit messy to explain what's going on. But if you ignore that, then all you have to do is, all I'm really saying is that, we take the a plus jb form and convert that into the a to the theta form, and then everything just drops out. So essentially what happens is that the unit circle maps to the left half plane. So this is z, and this is s, and this is real, this is imaginary. Same thing over here. So this left half plane is the same as the unit circle for z. And for z inverse, the opposite. Z inverse outside the unit circle is the left half plane. So when we say stability condition, we want to make sure that the sigma is in the left half plane, the roots in the left half plane. In this case, we'll say that z should be inside the unit circle, or z inverse should be outside the unit circle. Okay, either way, it's fine. Okay, any questions about this? Okay, so I'm going to quickly go through the properties of the Z transform, and these properties very much similar to the Laplace actually. I should add that the Laplace transform does not have duality. Okay, unlike the Fourier, the Laplace doesn't have duality, and the reason why Laplace doesn't have duality is because we have to intuitively what's going on is in the Laplace transform we have to kind of choose the sigma at which we're going to do the line integral. Okay, we're going to choose that sigma, and so that makes it mathematically difficult to invert. The form is not the same. The Fourier, the form is very much similar. In the same way, in the Z transform, the inversion is done with the circular integral. Okay, and so because of the circular integral, we don't have that nice equivalent of mathematical form. So duality, which in the Fourier case we say x j omega, this is duality with x of t. We don't have that with Laplace, and we don't have that with the Z transform. Instead, we have these nice properties. So the first one is linearity, and we've seen this many times, so I'm not going to explain exactly what it is, but it's pretty straightforward, and the proof of linearity is just trivial because you have an infinite sum. The second one is time shifting, and time shifting is a very standard operation in the time domain, in transforms. And the reason is because we want to take a signal nominally at 0 and we want to delay it. In all cases, what we're really going to do is multiply that by the complex frequency operator. So in the case of the Laplace, we multiply by e to the minus s t naught, where t naught is a time shift, so I think use small t. In this case, we're going to multiply by z to the minus a. We're going to shift by a steps. So x k minus a, we're shifting the time a steps to the right, and the Z transform is going to be z to the minus a x, like so. So you can just remember that the Fourier transform we multiply by e to the j minus j omega. In the Laplace transform we multiply by e to the s t naught, and so we just basically multiply by the equivalent. So this is Laplace, and in the Fourier it will be minus j omega t naught. In the z it will be z to the minus a. So it's always the same form where we essentially are going to use the time shift in the multiplication. And the frequency shift works the same way, and I don't think I've described that. The third one is scaling. Scaling is just like, scaling always works the same way as well. So scaling means that when you expand in the time domain, we compress in the frequency domain, and we are going to reduce the magnitude as well. Okay, we're going to reduce the magnitude as well. And the other way around, if you're going to expand in the frequency domain, you're going to contract in the time domain. So we just shift these two operators. So for that reason, I've just shown scaling in the Z domain. So we basically say that x 0 a, so I'm scaling it, I'm making it a times slower in the frequency domain that